Welcome to The Explainer. Today, we're going to tackle one of the most important inventions of the 20th century, the bipolar junction transistor. It's this tiny, tiny device that absolutely changed the world, and we're about to find out how.
So let's kick things off with a pretty simple question. How can you possibly control a massive flow with just a tiny, tiny touch? The answer to that, well, it's the secret sauce behind pretty much all of our modern electronics.
I want you to picture a regular water faucet. That tiny twist of the handle controls a much more powerful flow of water, right? Keep that simple idea in your head. A little bit of control creating a huge result. It's the perfect way to think about what we're about to dive into.
All right, so that principle of a small input controlling a large output, that is exactly how a transistor works. It's what makes it the ultimate tiny electronic valve.
So what exactly is a transistor? Well, to put it simply, it's a little semiconductor device that has two main jobs. It can act as a super fast switch, turning a current on or off, or, and this is crucial, it can be an amplifier, taking a small signal and making it much bigger.
So, how is this little magic device actually built? Okay, let's peel back the layers and take a look inside this electronic sandwich. Okay, so the bipolar junction transistor, or BJT, is made from 3 layers of semiconductor material, usually silicon. Now this silicon has been doped, which just means it's been treated with some tiny impurities to change how it conducts electricity. This gives us 2 types of material, p-type and n-type, and by sandwiching them together, either NPN or PNP, you create these 2 internal barriers called PN junctions, and those junctions are the key to the whole thing.
And this little sandwich has 3 connections, or terminals, and they line up perfectly with our faucet analogy. You've got the base, that's our control handle that we turn. You've got the collector, which is like the main water pipe, the source of the big flow. And then there's the emitter, and that's the outlet where the controlled flow comes pouring out.
Now, by sending a tiny electrical signal to the base, remember that's our control handle, we can get the transistor to operate in 3 totally distinct modes. It's just like turning that faucet to be completely off, fully on, or somewhere right in the middle.
First up, we've got cutoff. With absolutely no signal going to the base, the faucet is slammed shut. Nothing's getting through. No current flows from the collector to the emitter. In this state, the transistor is just an off switch. Simple as that. Then you have saturation. Now we send a strong signal to the base, and boom, the faucet is cranked wide open. The maximum possible current is just flooding through. In this case, the transistor is acting as an on switch. And now for the really cool part, the active region. See, here, it's not just on or off. We're carefully adjusting the flow. A tiny current going into the base precisely controls a much larger current flowing from the collector to the emitter. This is how a transistor becomes an amplifier. Now, to get the transistor into this powerful active mode, you have to apply some very specific voltages to bias it correctly. What this means is you're setting one of those internal junctions to allow current to flow easily, that's forward biased, while setting the other one to block current, or reverse biased. It's this very specific electrical setup that unlocks its amazing ability to amplify. So how do we actually set this thing up to be the perfect amplifier? Well, it's all about finding its operational sweet spot. It's a process that engineers call biasing. The key number that measures a transistor's amplifying power is called beta. It's a really simple ratio. It's the large output current you get from the collector divided by the tiny input current you put into the base. Basically, it just tells you exactly how much your signal is going to get boosted.
So how much amplification are we really talking about here? Well, a pretty typical transistor can have a beta value of over 200.
And what does that even mean? A beta of 200? It means a tiny electrical whisper going into the base comes out of the collector as a full-throated shout 200 times stronger. I mean, that is just incredible amplification from such a tiny little device.
But, and this is a really big but, to get this clean, undistorted amplification, you can't just flip it on. The transistor has to be set to a perfect idle state, all ready to respond to a signal. And that careful setup process, that's what we call biasing. This perfect idle state has a name, the quiescent point, or Q point for short. The best way to think about it is setting our faucet exactly halfway open. It's not off, and it's not fully on. It's just perfectly poised right in the middle, ready to amplify an incoming signal cleanly without making a mess of it.
All right, let's step back for a second and see how this one tiny component, with its simple functions, completely and totally reshaped our world.
You know, it all comes down to those two simple jobs. As a switch, you have billions of transistors flipping on and off, creating the ones and zeros that make up the logic in every single computer processor and memory chip. And as an amplifier, well, they boost the signals in everything from radios and your headphones to the most sensitive scientific instruments.
So just think about that. From this incredibly simple, free-layer sandwich of silicon, we get the two fundamental operations that built our entire digital world. It is no exaggeration to say it is one of the most impactful inventions in all of human history.
The transistor proved that a single, elegant solution to a fundamental problem, controlling a large flow with a small one, can change everything. Which really just leaves us with one final question to chew on. What's going to be the next tiny valve?